So just to give an idea of sort of how much stuff is inside a WISP, what we're talking about, I want to compare a standard AA battery versus a WISP. You can't see that too well, but don't worry about it. I'm just showing photos of those two things. So people in the census community would understand, 2,500 milliamp hour battery versus a 10 microfarad capacitor. Inside one of these batteries is almost 10 kilojoules of energy, and on the WISP's little capacitor, if you fill it up all the way, you have about 20 microjoules. So what's the difference? Well, there's a pretty big difference, 500 million times. It's obviously, you shouldn't obviously assume that there's just 20 microjoules in the capacitor, because it's not gonna always be either full or empty. When there's RFID reads going on, it's going to be sort of fluctuating. But we can use that as just sort of an idea of kind of a very loose bound. So how much is 20 microjoules? We measured the energy consumption of a no-op operation on the MSP430 on a WISP, and it was about a nanojoule per no-op. So that means that we can do roughly 20,000 no-ops, or get about 20,000 cycles worth of computation if we sort of fill up that imaginary perfect capacitor and let it just drain via computation. So that's enough to do maybe a couple matrix multiplications, maybe a little bit of AES. I'm showing 2 and 7,000 cycles for those operations respectively. So this is not a huge amount of computation. And so the lesson that we take away from that is that you can't really expect large computations, especially, we're in security, we think about crypto. We can't really expect large computations to finish without a fairly steady supply of energy coming from a reader. And that leads us to our next lesson, which is that you should be grateful for the energy that you get. And the sub-lesson there is that what you see in the lab might not equal what you get when you deploy an application. So the plot that I'm showing here is a trace of capacitor voltage as I move a WISP around in the field of a reader. So this is basically in a 3-foot cubic imaginary box, and I'm moving the WISP around and sort of dancing it in all sorts of different ways. It's kind of pathological. Yeah, I was trying to screw it up, but we can see how the bottom there is 0, and at the top there is a few volts. So really, all these vertical lines that we see are sort of death and resurrection of the WISP, and it's really difficult to compute in that model. So whenever you're up there, you should be happy. And there's a lot that's working against us here. There's the Friis equation. Thanks Friis. The quadratic fall off of RF energy as you get farther away from a reader. Just the fact that reader transmissions are bursty. Somebody in my lab likens trying to harvest energy from an RFID reader as being like trying to harvest solar from a strobe light. Multipath, which is a word I've heard only once today, but which really confounds a lot of your most naive thinking about this radio stuff. And I won't go through the rest of the list, but actually some of the things that are important for applications in the real world are occluding materials and things moving. So occluding materials, here's some anecdotal evidence. So Kevin showed this meat picture before, which sort of takes the steam out of this, but I can tell you that this was a WISP inside a Ziploc bag implanted between some ground beef and a layer of bacon to simulate a human torso. We were working with implantable medical devices. And we had this application that was doing essentially authentication as fast as it could. So it would do this computation and then beep a little piezo buzzer that was attached to it. And we could only get it to work reliably within about a foot of the we had the meat like on top of the reader, or sorry, we had the I was moving the meat with the reader inside around the antenna. It only worked within about a foot. And this concrete that I mentioned, it looks like we can only get between a 5 and 10 inch range so far. That's very preliminary, but that's a sort of a long way away from the kind of open space distances that we've been talking about so far. So things like water and other materials really limit the range that you can get. So the third lesson I'll talk about is is that you should use flash memory sparingly. And by use flash, I mean write and erase, which are the two expensive operations. So in the census community, people all know that you should avoid using your radio because it's expensive. Whether you're talking to other motes or you're talking to some sort of base station, like people do all these tricks to avoid using their radio too often. So what's analogous on the WISP? Let me give you some measurements that we've taken to give you an idea. So for 128 bytes, it takes about 96 nanojoules to move from memory to memory. On flash, it's a totally different story. Okay, that's 57 microjoules, which is, you can do the math. It's a whole lot more. Radio, on the other hand, it's actually less expensive than memory to flash. Now, I guess this is going to be, we've been talking about backscatter today, so I guess this is not as much of a surprise as it might otherwise have been. But we were certainly surprised when we learned that we could use the radio for sort of storage, as long as we, followed the right protocol, more cheaply than we could use the flash, the local non-volatile memory.
When you say radio, you mean backscatter?
Backscatter. I mean, yeah, radio communication, backscatter. And I'm not showing a number for ADC, but it's, as I recall, taking one ADC measurement is about the same amount of energy as writing one word to flash. So to answer that question, what we should avoid when we're on the WISP is avoiding flash write and erase. That's sort of analogous to the census problem of avoiding radio. And to give you some numbers to support that, this is from a paper that was in Usenix Security this year. It's a simplified version of a diagram from that paper, but essentially what it shows, that top line, the blue line, is the cost of is the energy consumption of writing to flash as the data size increases from 0 to 256 bytes. And you can see this crossover point where it crosses these other lines representing radio. And it turns out that above certain data sizes, it's much less expensive to use this backscatter instead of flash. And I believe it could be even cheaper if we use a different transistor for the backscatter. That we may be able to talk about that later. I need to move along though. The fourth lesson that I want to get to is about being defensive, and that's kind of a vague term, and I mean it in a couple of different ways. And here's a picture just to remind us of the sort of environment in which we're trying to operate. So one sense I mean reliability one sense I mean defensive is in that of reliability, right? So I mean defending against adverse effects of this constant power loss that you're dealing with. So we're developing a system in my lab called Mementos. We presented it once, and we have another version, much more complete version, going to be in submission soon. But the gist of it is that Mementos is a collection of compiler techniques and also some runtime tricks to enable automatic execution checkpointing during the running of some application on the WISP. So essentially, it's taking computations that maybe would require more energy than you have in a single life cycle of awakeness. And an example of that is just that, if you have like this 32-bit modular exponentiation, for example, you might break it up into two pieces in order to get it done in two different life cycles, with a power loss in between. And the whole point of Mementos, what it does, the way it differs from other checkpointing systems is that it assumes that reboots are the rule rather than the exception. So, not an unusual condition to find yourself rebooting. I just mentioned it, but CCCP, this paper that was in Usenix Security this year, it's an extension of Mementos in that we're using something instead of non-volatile RAM to store execution checkpoints. In this case, we're using backscatter. We developed this really simple security protocol that allows us allows a tag to entirely avoid trusting the reader infrastructure. So, you take your checkpoint of your execution, you encrypt it, and you MAC it so you have some authentication. And it exploits the idea that radio is cheaper than flash. Skip the last bullet, but this protocol diagram just shows how you have to structure your protocols, or at least how we found you have to structure a protocol if you're working in this regime in which one party has to initiate the communication and the other can only respond.